So one more time. An isotope is the average of the masses of all of those elements which are the same. And AMU is the atomic mass unit, which is 1/12 of the mass of carbon-12. The proton is considered to be 1, and a neutron is considered to be 1, and an electron is 0 portion of it. Let's stop though. Another way, if for those of us who are kind of confused or not accepting that why electrons are considered to be 0, the atomic masses comes from the neutron of that atom, which consists of protons and neutrons, not any electrons. Those are on the outside of that atom. It says here, usually not a whole number, since it is weighed as an average. Bless you so much. Remember, just like your grade, if you got one grade for the whole semester, that 88, that's what you got. It was a whole number. But if you had anything more than one grade, if you had 2, 3, 4, or 5 grades averaged together, you would get a decimal point. Now, the equation for AMU, or for average atomic mass, that's an O, equals the percent abundance, or abundant, times the mass number, plus the percent abundant times the mass number of the second one, plus the percent abundance times the mass number of the third one, dot, 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 dot. However many you have. If you have 7 isotopes, you would do these parentheses 7 different times. If you only have 3, then you would do those parentheses 3 different times. These are isotope number 1, so if you want to, you can, at the top, you can call this isotope number 1 plus isotope number 2 plus isotope number 3 to help you out later on. If you forget what this is. What is this, Miss Munson? This is isotope 1 plus isotope 2 plus isotope 3 plus isotope 4. You know, let's hope there's only 2 or 3 isotopes, okay? If not, then you'll do this 7 times and there's 7 isotopes. It's an average. You end up with that decimal point. So let's go ahead and figure out how they get those decimal points on the periodic table. It says let's calculate the average atomic mass for chlorine if it contains 2 naturally occurring isotopes. I'm going to, just in case, because I feel like somebody's going to forget later on. This one right here is going to be isotope, number 1. This one right here is isotope number 2. This is right here is isotope number 3, dot, dot, dot. Okay, you're going to do that for however many isotopes. Now, example number 1 says that there's only 2 isotopes. Oh, yes. So that means I'm going to do this equation only 2 times and add them together. That's it. Here are the isotopes over here. Isotope number 1 and isotope number 2. Does it matter which one you put in the first parentheses? No, because I'm just going to add them up at the end. Does not matter. So let's go ahead. Percent abundance, which is, here it is, percent abundance, 75.77. Now, can you multiply a percent sign? No, you have to turn it into a what? There you go. Turn into, just in case, so I'm writing these extra notes when you're not in class with me, turn into a decimal point. I know I misspelt it. That's horrible. So I'm going to come over here and I'm going to find a different color. I think this is red. Oops. And I'm going to say 1, 2, because you know that you need to move the decimal point 2 places over. So now that truly becomes 0.7577. I'm going to put an X right here because that is no longer a decimal point. Or I can erase it just in case. I'd hate for someone to confuse this when they're not in class with me. So I can do that. Move that decimal place over, multiply this, because that's what it says right here, multiply it by the mass number, and the mass number is right here at the top. We all know that. That's what that number is, 35. Now all of this is going to become one part of it plus, 0.2423. I'm going to just put a little arrow. Move over 2 places. So that way when you're not in class with me, hopefully that makes sense. That's why that number is 0.2423 times 37 equals my AMU. So 0.7577 times 35 comes out to a number, plus 0.2423 times 37 comes out to a number. If I was you, I would double check me because I am not always right. I'm probably more wrong than I am right. 26.52 plus 8.97. I'm going to pause for a moment. Let's say you're taking this crazy hard class. 75% of your grades that you've been taking or making in class, you have been getting 35s. This crazy hard class. 24% of the time you've been making 37s. If I had to guess where your average or what your grade is going to look like, wouldn't it be closer to the 35 than the 37? Because 75% of your grades are 35s. Does that make sense? So think about that before you actually do the math. Now we can go ahead and add those together, and when I add those together, I don't have my number. What'd you get, Daniel?
35.49. 35.49.
AMU. Okay, so you can see that it's going to be closer to the 35 because 75% of the chlorine that has been found has been the chlorine 35 mass, not the chlorine 37. There's only been 24%. And shouldn't those two numbers equal 100? 75.77 plus 24.23 should equal pretty close to 100, if not 100. Alrighty, let's do this again. I really think this is pretty easy, so this should be pretty easy for our homework. There are 2 isotopes of copper. Yes, I don't like to do a lot, so 2. This is copper 63 that has an abundance of 69.1%, and copper 65 has an abundance of 30.9%. Before we do any math, we can see 69 percent, 0.1, which is more than 30%, is the 63 copper. So our number should be closer to the 63. So let's go ahead and do this. I've got 0.691 times 63, and I just, because this one's first, that's the only reason why I did it first, plus 0.309 times 65 equals blank AMU. So then I'm going to get this number once I multiply them plus this number equals blank AMU. Not too bad? Hopefully that's easy cheesy. Easy equation. Now we can definitely feel comfortable when it comes to the quiz next time you come on Wednesday, but we're going to go over that homework to make sure you did it right. You got to practice. And then we get to this next portion over here, which is going to be that next part of that homework page that we're going to do. It says here that chemists count by moles. So kind of like, you know, when you were younger, you learned like 1, 2, 3, 4, 5. And then when you got a little bit older, you learned how to count by 2s, 3s, 5s, 10s, right? Okay. So now we're learning how to count by moles. Okay? Imagine how you counted by 2s, by 5s, by 10s. Now you're going to learn how to count by moles, or an abbreviation is MOL. I know, it's almost spelling the whole word, but that's just the abbreviation. Okay? Doesn't matter whether or not you're a chemist or whether or not you are doing whatever it is, medical science, pharmaceutical, in the U.S. or in another continent. This is how people in chemistry count. Now, when we're doing this, we need to know a couple of things. Number one, what's important is this actual number of a mole. A mole is considered to be what we call Avogadro's number. And Avogadro's number equals 6.02 times 10 to the 23rd. That is a huge number. That is nothing like counting by 2s or by 5s or by 10s. Now we're counting by Avogadro's numbers in chemistry. Avogadro's number is 6.02 times 10 to the 23rd power. That would be moving that decimal place right there 23 places to the right to make it a big number. That is a lot. So Avogadro's number is 6.02 times 10 to the 23rd power, which equals 1 mole of anything. Okay? So if they say it's 1 mole, then it's this many. That is the number. It's huge. If they say 5 moles, then it's this number times 5.
How would you times that by 5?
Say it again.
How would you times that by 5?
Oh, good call. Can I? Here we go. Pause for a moment. That is a good question. In your calculator, I'm going to clear this out. I'm going to parentheses 6.02. Do you see up here the second key? I'm going to come over here to the comma that's above the 7 to the 23rd power. Close parentheses times 5 equals 5 moles. That was a great question. How do I even put that into the calculator? 6.02. I hit second key, comma, 23rd. That little e means times 10 to the. That puts it into an exponent. In math class, you may have used that little house top, and that's completely A-okay. Yes, sir?
Did you forget the times 10 in that equation?
Nope, it's right here. The e to the 23rd is the times 10. One more time. This e, which is second key comma, means the same thing as the times 10 to the 23rd times 5, 3.01 to the exponent of 24, which is times 10 to the 24th power. So that was a great question. Back to you. Thank you, sir. I appreciate it. So Avogadro's number. Next part over here. The next thing we need to know when it comes to this is number 2. SI unit for the amount of substance. Oops. Avogadro's number stands for or represents, it's the SI unit for the substance. Number 3, the next thing that we need to know is the mole is used to count atoms or molecules, which is represented as MC, or formula units. Which is represented as FUNs, comma, which are tiny. Can you imagine an atom, how tiny one atom is? I mean, you know, yeah, exactly. That's one atom. Because it's so tiny, so small, that's the reason why we have so many before we call it one. That makes sense. Because it's so tiny, so small, we get this much before we call it one. Okay? They are so tiny, so you need a lot before they become visible, before you can see a piece of gold, before you can see a piece of aluminum. They're so, so tiny. And because they're so, so tiny, in chemistry, we just couldn't even just count them out like by 1, 2. Oh, we got 10 atoms. Those are still so tiny, we can't visibly see it with our eyes. Because of that, now we call it 1 mole. Yes, sir.
So you tell me, you mentioned like,
Mhm.
what do you do, but you tell me how could we get like inhale the gold atoms?
Oh, you inhale a whole bunch of different atoms, you know, all the time and not know because they're so, so tiny. I agree, 1,000%. Thank goodness for our body being smart enough to know what to get out and what to keep in. I agree 1,000%.
I wouldn't tell you that.
You want to be good, right? Right? So hopefully that makes sense that they are so, so small that we have to get such a big amount before we can call it one, which is 1 mole. The next part, which is part of your homework here, is representative particles. We've got 3 types of representative particles. We have atoms, which we already talked about over here. Atoms, or formula units, or molecules. So let's talk a little bit more details about those different types of representative units. Number 1, atoms. Obviously, atoms are going to be those elements that are not bonded. Unless they're going to be the diatomics. Don't forget there's 7 diatomics, but we still consider them to be individual atoms. They are not considered to be bonded, even though they are come together as a pair. One more time. Don't forget, atoms are going to be the elements on the periodic table that are not bonded, except we have those 7 diatomics. Even though they are quote-unquote bonded together, they are still considered to be free atoms that are by themselves. Molecules. Molecules, you know, are compounds that are made of only, and this is the key word, non-metals. For an example, we have CO2, carbon dioxide, H2O, dihydrogen monoxide, and O2, which I take back what I just said. I said those diatomics. Let's put those diatomics into the molecules. Forgive me for that one. I spoke too soon on that. Which there are 7 diatomics. Non-metals. Miss Munson, which ones are those non-metals? Those are going to be this side of the stair steps. They do not touch the stair steps. They're on that side of the stair steps, but they do not touch the stair steps. Those are going to be our molecules. And then the last one, our formula unit. Our formula units are going to also be compounds, but they are going to be made of metals and nonmetals that are bonded together. For an example, table salt, sodium chloride, table salt, sodium chloride. This is the metal and that is the nonmetal. This is the metal and that is the nonmetal. Now your homework says, well, add them up. So let's get to the adding up, which obviously you're going to need your calculator, and then we'll be done with our notes. Trying to see, good, we're still on good timing. So it says here, let's look at the mass when we're talking about these moles, okay? Now, as a quick reminder, for an example, if we were to look at carbon-12 on a periodic chart or periodic table, carbon, why did I put 12? I don't know. Who else is 12? Let's do that. Let's go find who else is 12.
The other 12 is
Magnesium.
magnesium, yeah.
Let's do that. I can just change that. Magnesium has an atomic mass of 24.305. We know that the top number on the periodic table is the atomic number. The bottom number on the periodic table, you already know, is the,
Number or
yep.
average mass number.
But, or AMU, or, here's the new word we're bringing up, molar mass.
Would that be like molecular mass?
Molecular mass, molar mass. That's another word it could be called. So, for an example, if that's the periodic table of 12, on the periodic table, we have magnesium 12. The atomic number, which is on the top, which is the number of positive protons as well as negative electrons, because all atoms are considered electrically neutral, unless otherwise stated. The bottom number, which is an average, AMU, that's the reason why we have our decimal point. Why? Why do we have the decimal point?
Because it's averaging the isotopes.
Multiple of the isotopes averaged together. And we also call that the molar mass. The molar mass, let's look at that definition or that vocab word. The molar mass is the mass of 1 mole of a substance. So what we're saying, and to me, this is where, again, I think the periodic table is so cool. We were to get magnesium, which we would not be able to get magnesium and just put it inside this classroom because it's extremely reactive and it would blow up. But you can get magnesium in a container and keep it in there because we don't want it out in the environment. But if we've got 24.305 grams of magnesium and put it on a scale, that would equal 1 mole of it, which equals 6.02 times 10 to the 23rd atoms of it. That's how we count in chemistry class. One more time. I need this to sink into your head so you can visualize it. This is what is so hard about chemistry class versus, for an example, me teaching physics. If I'm teaching physics, we can build it and we can make it and we can make it do something. But in chemistry class, it's a little harder. Okay, so let's stop one more time. Magnesium is on the periodic table. Magnesium is an element. It's a metal element. It is in group 2, okay? If we got a scale, which we can grab a scale, we can put some magnesium inside of that scale. 24.305 grams of magnesium, put it on the scale, that would equal the molar mass. The molar mass is equal to 1 mole of it, which means that right there, however much substance I had, that means that right there in front of me, I had 6.02 times 10 to the 23rd atoms, or Avogadro's number, in front of me. That's how we need to learn how to start counting now in chemistry class. Okay? Now, that is what we said regarding, for an example, an element on the periodic table. Okay? The next thing that we have over here is, let's talk about elements versus compounds. We know that the elements are found on the periodic table, and compounds, and that's easy. All you have to do is look at the mass number. That's easy. You want to know what the molar mass of aluminum is? Go to the periodic table and then look at it. Okay? We want to know what the molar mass of lithium is? It's 6.941. Go to the periodic table, find the atomic mass, and that is 1 molar mass of it. Easy cheesy. But if you're looking at compounds, you have to do a little bit of math. It's not hard. It's pretty easy. Okay? When it's a compound, you're going to, for an example, let's say it's compound XY3. Again, this is just an example. There's no compound of XY3. We're just representing it. How we look this up, or how we do this math, is we're going to get, for an example, how many X's do I have? Well, behind it, that little number tells me how many atoms. So how many atoms of X? I have 1. So I'm going to go ahead and count that as 1. I'm going to go to the periodic table, and I'm going to find the mass number, which equals blah, 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 decimal, blah, blah, blah. Again, pretend numbers. I'm going to go to the Y. I have 3. That's a little 3. I'm going to go to the periodic table to get that mass number. And I'm going to get the blah, 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 decimal, blah, 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 and I'm going to multiply it by 3. I'm going to add them all together. It's not hard. It's really easy cheesy, and we're about to practice it. This is just like the homework. The homework is going to ask you, what is 1 mole of aluminum? Aluminum's in group 13. So when we look at the periodic table and we look at group 13, aluminum also touches the stairs. 26.982. So what is a molar mass of aluminum? 26.982 grams per mole equals 1 mole of aluminum. Okay? Let's do it again, though. We're going to do it for carbon dioxide. Whoa, carbon dioxide. I'm going to pause real quick. Here's carbon and here's oxygen. They are both on this side of the stair steps, which means that they are going to be a molecule right here because they're both nonmetals. So let's add it all up together. How many carbon atoms? 1. How many oxygens? 2. I'm going to multiply it by the, remember how I said over here? Mass number from the periodic table. Come over here to carbon, which is a nonmetal. Mass number is 12.011. 12.011. Oxygen, which is 15.999. 15.999. You could, absolutely. I don't blame it if you say 16. We're going to go ahead and multiply it together. 12.011 times 1 is 12.011. 16 times 2 comes out to 32.000. Add them together, 44.01 grams per mole equals 1 mole of CO2, which so happens to be a molecule. Easy, easy.
One question is a bit far back. Why on Earth
Uh-huh.
is that Avogadro number so much bigger than just the normal mole? It just doesn't make sense to me.
What do
Why?
you mean so much bigger than the normal mole? It is 1 mole.
So that is 1 mole?
That is 1 mole. Avogadro's number is 1 mole.
That is. Never mind.
Avogadro's number is 1 mole. Let's do this again. But this one is considered to be an FUN, or a formula unit. Why? Because we have a metal and nonmetals that are bonded together. First step is we need to count how many atoms we have of each. Well, I can see that I have CUs, I have Ns, and I have Os. How do I know? Remember on our homework I said, hey, if it's 2 letters, make sure the first letter is a capital so that way you can distinguish the different elements. Okay, CU, Ns, and Os. The little number behind it is the number of atoms you have. But in this situation, I have a parentheses. When I have parentheses, it's almost like math class when you used to do factoring. This 2 goes here as well as here. It does not go to the CU. How many CUs do I have? Look behind it, just 1. How many N's do I have? 2. How many O's? 4. There you go. Absolutely correct. Now we go to the periodic table to find the mass number. So Cu, which is copper, it's a metal, it's right here. Copper is number 29, 63.546. 63.546. Nitrogen, it's a nonmetal, 14.007. 14.007. Oxygen, we've already said we're going to round it to 16.000. So those two, what we're going to do is we're going to multiply those. I guess I should have did that. 63.546 times 1 is 63.546. 14.007 times 2, I've got something like, and your numbers may be a little bit off depending on how I round it, 28.02. I rounded that second digit to a 1. I did that last year. In here, 16 times 4 is 64.000. Add all of those together. Double check my math. Again, we might be off on the hundredths spot or thousandth spot, but I got 155.57 grams per mole, which equals 1 mole of Cu parentheses NO2 parentheses 2. There you go. Just depending on how far out you rounded.
The 6 probably goes forever.
Again, yeah, I don't know how far people go out. I like to go to the second digit. Easy cheesy? Easy cheesy. That covers our homework number 3. And again, don't forget, we swapped it and switched up our homeworks just a little bit